So thank you very much. I will give a talk on the board, or all my mini course will be on the board, because then I will be slower. So can I turn on the lights here in front of the board? I think then one can see it better. Thank you. So first of all, thank you very much for organizing the conference. It's a great pleasure to be here and to see a lot of friends again, and to talk to you in the breaks, and I'm really looking forward to it. So maybe the first intention from the organizers were that I should talk about my work related to quantum field theory on non-commutative spaces, but I decided to talk about something else, which I call the XY symplectic transformation in topological recursion. I don't want to write it out, such a long word. So TR is for topological recursion, and also, if I have enough time at the end, show how you can apply it, so end applications. Since this mini course should be introductory, my first lecture will be just about topological recursion and some properties. The second lecture will be about the XY symplectic transformation formula, and the third one about the Laplace transform of it, which can give us nice formulas for applications. Okay, good. So, as I said, today we'll just talk about topological recursion to bring everybody on the same page, and that we all know if somebody's talking about some differentials, multi-differential correlators, that we talk about the same things. The mini course is about this new formula, which is related to some kind of transformation you can do in this theory of topological recursion. And this new formula was computed, and it's quite interesting. It seems quite complicated, but it's actually very explicit, and we can compute intersection numbers on moduli spaces of the complex curves. This formula relates higher order free cumulants and moments and free probabilities, so it's a very powerful formula. And this is why I want to explain it in very detail in this course. And I think this is actually a nice thing to do because I have a lot of time, I can do examples, etc. But first of all, we know that topological recursion is related, this is why we are all here from all these different areas, is related to a lot of different things, like intersection numbers on MGN bar, Hurwitz theory, which is related to intersection numbers, of course. Then there's also free probability. Then there are matrix models. This is where it comes from. All these areas are not unrelated, but they have like one common greatest denominator, which is topological recursion. Then you can count maps. You can have what I worked in my past, quantum field theories on non-commutative geometry. Then more recently, we have also resurgence, where there was actually a conference just a few weeks ago in Japan. Then there's also quantum knot theory. Integrability, the integrable system. This formula I want to present comes originally from Hurwitz theory. People also here in the audience have computed it. It's related to weighted double Hurwitz numbers, and it's applied in free probability. It can be applied in intersection theory. It has a very great meaning in matrix models, also in this counting maps. So, and we're really looking forward to apply this formula more in all the other areas and see what it does. Because this XY symplectic transformation formula is a property intrinsically in topological recursion. And we know then that it has applications, it gives you new properties in all its type of applications. Okay, but let's start and say, or what is topological recursion? Now I want to define it. So as a slogan, you can think of topological recursion is an algorithm that generates from the spectral curve a family of multi-differentials denoted by omega gn. So this is the slogan. So we have some initial data, which is the spectral curve, and we have a universal structure, a universal formula topological recursion, which gives you this omega gns, and depending on the spectral curve, these multi-differentials encode something you're interested in. For instance, how many maps you can have for a sphere with one boundary and which is triangulated, or in matrix models, or in Hurwitz numbers, etc. But what is the spectral curve? Let's define it. So the spectral curve is the tuple sigma x y e with the following properties. So sigma is, in my talk, compact, connected Riemann surface of genus G bar. So this genus is a different G than this one. This is quite important. Then since we have a Riemann surface of a genus, we can choose a symplectic basis on it, which is written as these two cycles, independent two cycles, AI and BI. This is the symplectic basis of cycles. Then what do we have next? X and Y. There are two maps going from sigma to C, which I assume are meromorphic. They have critical points, which are usually called ramification points. These points are simple and distinct. So the points from X are not the same as the critical points of Y. So in other words, let's say we have, so these points are for X, I call them alpha I of X. This means that we have dx alpha I is equal to 0, and the points for y are, I call beta j, which means that dy of beta j is equal to 0. And this additional condition that they're distinct means that dx of the beta j is not equal to 0 and dy of the alpha I is not equal to 0. Good. Then what simple means, I can draw it in a minute, a picture, but it means like that just two branches come together at this ramification point, which is, if you pull it back on the Riemann surface, which is at the branch point, so two branches come together and not more. So the inverse is locally like a square root. And B is usually called the Bergman kernel in the theory of topological recursion. This is a symmetric bidifferential on sigma squared with a double pole on the diagonal and regular everywhere else, and also like bi-residue is equal to 1. I will show you how it looks like. And then it's normalized with respect to the A cycles, these AIs. So it means that you can integrate along an A cycle this form. This is 0. And also that the bi-residue is 1, which means that it goes locally it's like a symmetric tensor product, but I will not write it. 1 minus E2 squared plus some holomorphic part. So and actually if hello? Okay, can you still hear me? Yeah? Okay. So, and if we have a genus 0 spectral curve, which means that the genus of this compact connected Riemann surface is 0, this bidifferential is of this form, because we cannot have any additional holomorphic function on a compact Riemann surface of genus 0. Okay, this is the spectral curve. So we have this 4 ingredients. And from this, we define all omega GNs, which are formulated in the slogan above. But first of all, maybe a picture. This is all the time good. So sorry for those who have seen this picture thousands of times, but we have, let's say we have here our curve, sigma, and here the real part of the projection with respect to x, and here with respect to y. Then we have here a point, which is called the ramification point. This critical point is, let's say, alpha 1. This is alpha 2. So the first derivative is 0 at it, so it's like a tangential point. So here we have the branch point, and above this point we see that two branches come exactly together, sigma, and here's another, let's write it first, sigma prime. They come together, and the assumption that this is simple means that we have just at most two branches coming together, or just two branches coming together at each ramification point. But we can see above there's probably a third branch And then here we have another point. If we look here above, we can see that actually two other branches are coming together at this point. So this is a picture you should have in mind. Something else? No? That's it. And then, how are we now defining all the omega GNs? So this is now the definition omega GN. For G and N positive integers, we define the multi-differentials omega Gn on sigma n. Yeah.
In the case of elliptic curves, is there a formula for Bellman curve also?
There's an explicit formula, yeah. So if you, there's one additional condition, right? That you should fix this one additional cycle. It can be written in terms of the Weierstrass P function. And there's an explicit formula for that, yeah. And even for higher, you can write it in certain types of theta functions. But it's very ugly and not very explicit. Other questions? Yeah, by the way, if anybody has a question, please ask and interrupt me at any time. Yeah, please.
Why is it called a spectral curve?
So I think I actually don't know the right origin of this, but my idea is that it's first of all a complex curve, an algebraic curve. You can see it as an algebraic curve, but it comes from matrix models. And this information here encodes the spectrum of the matrix model. So the spectrum of the eigenvalues. So it's like a mixture of spectrum and complex curve. I don't know if this is right. Other experts on topological recursion has other ideas on that? So yeah, so this is where it comes from, the matrix models. And if you want to solve the first topology, which is G equals 0 and N equal 1, and this gives you the information how the eigenvalues are distributed. So this is information about the spectrum. And this forms an algebraic curve. So
isn't it the relation between the spectrum and the Cauchy transform? Isn't that what it how it's a spectrum?
Yeah. Okay. Yeah, that's right. You can also.
It turns out, in some cases that's an algebraic. It satisfies an algebraic equation.
Yeah, that's right.
And
so if
the
I
algebraic equation is this curve.
Yeah, so I can.
The spectrum for the.
Yeah, that's right. That's completely right. So I can write a polynomial. So an algebraic equation. Which is equal to 0. So this is an algebraic. So if we assume that these two functions are meromorphic for all z on sigma, we can find a polynomial equation such that this is satisfied. So we have an algebraic equation. So this is where it comes from, the curve. So an algebraic curve, which encodes the information about the spectrum. Okay, so then let us define. So I said maybe positive, then let's write here +1 and +1. So, and then omega 0, 1 is usually defined as the function y dx. But you could also use another one. I will comment on that maybe later in the talk. Oh, I don't have actually so much time. Oh, maybe we started a little bit late. So an omega 0, 2 is the Bergman kernel, and then we define recursively in 2g plus n minus 1 then, because I have this small shift, greater 0, all omega gn plus 1 in the local coordinates z and zi, where set I are, let's write it. So this is z1 up to zn. This is like a shorthand notation for that. And then we sum over all alpha i's, which were the ramification points of x. We take the residue of the kernel this way of omega g minus 1 n plus 2 q sigma alpha I of q zi plus the sum over all g1 equal to g I1 I2 is equal to I, but I gi and I is not equal to 0. Empty set, and here we have g1 I1 plus 1 q I1. Sorry, that's a quite long formula. So this is the definition for omega gn plus 1 recursively in terms of all the other omega gn's which have less topology, let's say, which have less negative Euler characteristic, and the kernel is of the form that we integrate from this q omega 0 2 omega 0 1 q minus omega 0 1 sigma alpha of q. So what I have not defined is this map sigma alpha, and this is called, let's write it here, is the local Galois involution. It's a local deck transformation. So which means that we have this point z here, and it maps to this point here, which is sigma alpha I of z, and they are the same points here below. So this is an involution because we have just two branches coming together, and they have the condition x of z is x of sigma alpha I of z with the fixed point alpha I, which means sigma alpha I of alpha I is alpha I. Okay, so this is the definition of topological recursion. So you start with a spectral curve, and then you define omega 0, 1 in this way, omega 0, 2 with the Bergman kernel, and then the rest is computed recursively by this formula. Okay, let's look at this formula for a second, and we see that the kernel is completely defined through the spectral curve. So we have here the omega 0, 1 entering, which is defined through y and x. And here above we have the Bergman kernel, which is defined through b. And there's a picture you should have in mind for topological recursion, which is that, this is on Wikipedia, that your omega gn plus 1, you can see it as another Riemann surface of genus. G is 2 in this case, so this is omega gn plus 1. Here we have the variable z at the boundary, or if you want to think as a boundary, and here we have all the other ones. And what does this formula? It decomposes this object into something else. Let's do one more here. So this is our omega g n minus 1 n plus 2. So this is like this term entering this equation, this pair of pens, you can think of the kernel, plus another set of possible decompositions, which is this composition. So we have again the kernel times this 2 omega g1, omega g2 with the different sets, I1, I2, here g1, g2. And you sum over all possible decompositions except this one condition here. So this is a nice picture. I mean, why does this picture, or where does a picture come from? It actually comes from matrix models and counting maps, where you actually count triangulation, quadrangulation of such kind of spaces, such kind of maps, and they satisfy this recursive equation, and the solution is given by topological recursion. Okay, I really don't have so much time, so yeah.
Does this formula hold still if you change it? You sort of comment that this omega 0,1 was sort of a choice.
Yeah.
Does the kernel, how does the formula change?
Yeah, this comes now with the properties. This is important. So you can have changes for the definition of omega 0,1. For instance, okay, I will do it here in a minute. So let's first list some properties, and then at the end of the list of the properties, I will comment on that. So what kind of properties do we have? So first of all, omega gn is symmetric. So the formula is obviously non-symmetric, so we have like one distinguished variable z here. Also in this picture, the left-hand side, the left boundary is distinguished, and the other one not, but you can show that it's actually, it generates symmetric multidifferentials by just iterating this formula. Then you have to, exchange the residues, you move the contours, pick up the right poles, etc., and you see that it's symmetric. Then for 2g plus n minus 2, for negative Euler characteristic, if you wish, the omega gn's have just poles at the alpha i's, which were the points, which were the ramification points of y, which is not true for omega 0,2, where it has a pole on the diagonal, and also not for omega 0,1. Then there's something called the dilaton equation. So where we have, sorry? The order of the, you have a maximal order of the poles, which is, I don't know, 6g minus 6 plus 2n or something like that, maximal order. And if you compute this equation, it gives you the omega gn's a very nice partial fraction decomposition. So you really can read out all the poles and the coefficients of the poles. So you have to run the formula once by yourself or with the computer, and you can see how the different poles are generated. There are different things. If the spectral curve is irregular, then you have poles of lower order, but the highest order is something like 6g minus 6 plus 2n, probably. Something like 2 times the dimension of the modular space. Homogeneous G with MR, something like this. So, highest order pole for the situation. And then there's a formula for going back one topology if you want. Yeah, 2 minus 2g minus n. We take the residue of omega gn plus 1 q zi times some function. I will call it in this way due to later convention in my next talks. So we can like destroy one of the boundaries if you wish by taking all the residues, summing all over them over this function, where this one defined by an integral over from some base point to q of omega 0, 1. And I write it with this function of x of z, of q, because it's more convenient for later terms, but you can also just leave the x here. But later we will have better ways of writing something. So, and more importantly, there's something which is called the free energy, which you can think of omega G0, which is defined also by this formula. 2 minus 2g omega G1 times the phi 0, 1. And this definition holds for g greater or equal to 0. And this gives you like the free energies in the matrix model if you want, like the connected maps you want to count without a boundary. And what happens if you now transform y with some constant lambda y? G is greater or equal to 2. Yeah, this is the genus, yeah. So look, what happens if you transform y, or you multiply y just with some constant? You can look at this recursion and you just see that it appears here in the denominator, essentially, and this transform the omega gn by lambda 2 minus 2g minus n omega gn. So this is one possible way of transforming something. And there's a completely class of transformations. It's called the symplectic transformations. So this class of transformations leaves this form, this symplectic form, invariant. So we look at transformation which satisfies this, and these transformations are generated by three different classes. So you have x, y can be transformed to x, y plus some rational function depending on x. So this is one possible transformation. If we look at the definition, omega 0, 1 changes completely. Omega 0, 2 not. But where does omega 0, 1 enter the recursion? It's just here in the denominator. So, and if we change y by y plus some rational function depending on x, we would change this plus r of x of q, and this here minus r of. So we would change the omega 0, 1 minus q minus omega 0, 1 sigma of q. Let's change it. And this is actually, after this transformation, the same. This is the important point. Without sigma of q. This is because the Galois involution is, this sigma alpha is defined to be like the local deck transformation, and we see this is invariant. So Under this transformation, we have omega gn transforms to omega gn. Okay? So, but we can have a completely different polynomial equation. An algebraic equation can be completely different, but it preserves the omega gn's, then this, some rational function. Function in x. So we can have some kind of rational function, whatever you want. Then there's the transformation x plus b over c x plus d. And y is transformed x plus d squared over a d minus b c y. So where b, c, d are some complex numbers, let's say. So this actually comes from like an SL2C transformation. And also under this transformation, it's not directly clear, but also under this transformation, the omega gn's are preserved. You can check it. You take like the derivative of the first one, which generates exactly the inverse of this object. Here in the denominator, it works everything out, but I will not show that because I don't have enough time. But then there's the third transformation, which is the most interesting one, which just transforms x and y up to a sign. So this transformation preserves the polynomial equation. So it's like, it seems like the easiest transformation for this symplectic transformation, but it transforms the omega gn's in completely different objects. So they are again multi-differentials, but they have a completely different form. Before, we had this property that this object has poles at the alpha i's, the ramification points of x, and this object have now poles at the beta j's, the ramification points of y. So they're completely different. And the interesting thing is that under all these transformations, the FGs are invariant up to maybe some normalization constant, and as I said, for meromorphic x and y's. And this is trivial in this setting here above, more or less. But in this setting here below, this is completely non-trivial, that after this transformation, this omega gn's, we would take the residues over all the ramification points of y instead of x. This is not trivial. And I think it's proven for this setting, for these meromorphic functions. And this is also why these FGs are sometimes called symplectic invariants. And what I want to present in the next talks is the, how much time? 25 minutes. 25 minutes. Good. And what yeah, okay, good. I thought I have not. Okay, good. So, and what I present in the next talks is the relation between this object and this object. This is like the new insight we have, and there's an explicit relation between them, but it was quite abstract and just definition. What happens if we look at examples? So I want to do now some examples where maybe in the
what's the importance of the
the scale transformation, I mean, it just rescales it. If we transform x and y to y and x, we should include one minus sign because the wedge product is antisymmetric. And so you can include it. So you can do a mix of this one with this one to have like this x and y to swap. But it also tells you, for instance, this scale transformation there, how many steps you need to apply this recursive equation to get to this omega gn. It's exactly like the Euler characteristic. So let's look at examples. So for all of my examples, we have G bar is equal to 0, which means that this spectral curve is of genus 0. Actually, most of the examples on the market at the moment are in this case. There are just, I think, quite a few where you have non-trivial genus. And here also the Bergman kernel is given by, as I said, classical objects with some local coordinates, which you can choose on the Riemann sphere then. And then what kind of spectral curve we can have here. And what does it encode? So we have genus 0, so this is the P1, so this is the complex projective line, or the Riemann sphere, if you wish. We have x of z is given by z squared over 2, y of z equal to z, and b as here. This one is called the Airy curve. This is more or less the easiest example you can imagine. So what happens with your deck transformation? So first of all, what are the ramification points? They are at 0 and infinity. And what is the local deck transformation, which is actually a global one, z minus z. Because x of z is equal to x of minus z. What does it compute? Already very interesting things. So the omega GNs, let's say in the variable C1 up to Zn. Is it big enough? I hope so, yeah. Gives you a sum, K1 up to Kn, is equal to 3G plus n minus 3, which is the complex dimension of mgn bar, by the way, of the integral of mgn bar, the compactified modular space of complex curves of genus G curves with n marked points. Maybe we will hear about that also in other lectures, I hope so. Of the psi classes. And then we have here product of 2ki plus 1 double factorial over zi to 2ki plus 2, yeah, dzi. So maybe I will not comment too much on it. So you have this modular space of complex curves, which is of a lot of interest in algebraic geometry. It was probably someone already known to Riemann, or at least the dimension. And you can construct forms on it, which is, this is like a two form. This is the psi class, which is essentially the first Chern class of the line bundle of the in this nth of the nth line bundle, where the fiber is the cotangent space at the nth mark point. So there's a nice construction of it. I don't want to go into details, but these objects here are rational numbers. And it's quite interesting because they are very complicated to compute actually from algebraic geometry point of view. But if you know that the omega GNs from this spectral curve, which are generated by this formula, generates these coefficients, which are this intersection number, it's a very easy task. And how do we know that? I mean, this goes essentially back to a work of Kontsevich, because Kontsevich proved that these intersection numbers are related to matrix models, and we know that matrix models are related to topological recursion. This is actually where it came from. So here's this very universal structure which computes you the intersection numbers in this example. What is important here? What happens if we change the role of x and y? So now let's look. Y is just the identity. So if we want to use this formula, we have here omega 0, 1 with this check is then given by x dy. We have changed the role. Omega 0, 2 check is b, is also omega 0, 2. This stays the same. But all the omega g n check with 2g plus n minus 2 greater than 0. So where we have to apply this formula. A 0. Why? The reason is y is the identity. It's not ramified. It does not give you a ramified covering, so we don't have any ramification points here. So this is trivial. And what I wanted to talk in my mini courses, the relation between the omega GNs and the omega GN check, which is in this example not trivial. It's already here quite complicated, the relation, because these two objects are not vanishing. And this gives you like a new formula for the omega GNs here, where we don't have to use this recursion, but it gives you a new, maybe more explicit formula, if you wish, for the omega GNs here. And maybe then also new formulas for the for the intersection numbers on moduli spaces. Then actually, if y is the identity, this holds all the time. So we can have here also more complicated rational functions of x. And if y is the identity, we have all the time that all the omega g and check vanish. Then another interesting example, which now relates to maps and to matrix models and free probability also. So, is there any question? Any question? And there is the spectral curve. We have x of z is equal to alpha plus gamma z plus 1 over z. Then I write it in this. Is sum over k vk z to the k. So this is like a polynomial to some highest degree d. And b. So this is related to the Hermitian one matrix model. What does it encode? It encodes, or it enumerates maps in the following sense, that you draw a map with some boundaries, with some genus, and then you look at triangulations, for instance, and you want to count them. How many triangulations are there? And the alpha, gamma on this side and the VKs are related to the TKs. So if you have, you can also have quadrangulations, or you have other n-gons. Let's say this is an n-gon, and you weight them by Tn. So you weight the faces here, and you have an implicit definition of these coefficients here, which you use here, which are defined through this face weights. And then the omega GNs, G1 up to Zn, if you like formally divide by the x, that's right, the x ends, so which means we just look at the function in front of the differentials. This is usually defined then as W x1 up to, let's write it this way first. TK is like, if you think of, it's the weight of this face. So you have then different, I mean, you want to count how many triangulation I have, or a quadrangulation, and for each face you give this. Yeah. And I mean, and these coefficients on the left-hand side here are implicitly defined through these TKs. It's quite complicated how they are defined if you want to do it explicitly. But okay, this is not important at the moment, so let's write it here. Sorry, WGN. And I put here an index 1 and n to distinguish them. So, and if we look at this function here on the left-hand side, which is a meromorphic function, we can look at its Laurent expansion at a certain point, which is in this point infinity, in this example. And then this gives you the sum over all maps, I call this maps n just, of ordinary maps. Where we have here like a product over all these TJs, this weights of the faces, and here's some, with some exponent depending on this map. And here we have x1 to the, okay, what here, yeah, k1 plus 1 up to xn to the kn plus 1. So if you look at the Laurent expansion at infinity, this gives you like an expansion of this object here. And if you look at the different boundaries, so k is the number of boundaries we had in this picture. Okay, I erased it, good. And the k1 up to kn gives you like the number, the length of the boundary. And here it computes you something which is called ordinary maps. I don't want to define it in details, but this is also, so essentially you use sum here over all the k1s up to kn's, and this is like a map indexed by k1 up to kn, and maybe a genus. Yeah, this is a better way. But what it also gives you, some factor, I don't know, depends on n. And then it gives you also the cumulant of, so you can also write it in terms of matrix models, and then you have here product going from 1 to n, traces of 1 over x1 minus m, and then we take the connected part. So it gives you also the resolvents, which are the generating series of correlators in matrix models, where the measure, which is uniformly invariant, depends or encodes the structure of these faces here. So this is like a and here's some factor of n, maybe. Sorry, I don't know this factor. So it gives you a relation between, first of all, so this relation is known, which is nothing new or something else, but it's interesting that topological recursion encodes this one, and this type of expectation value is also interesting in free probability, because this is essentially, after a small shift, the moment in free probability. Because if you expand it, let's do this, xi. If you expand it, you have k1 to some kn. Then we have here the product over the matrices ki, product over I. And here you have divided by up to some symmetry factor, some prefactor, maybe k1 plus 1 up to kn, xn to the kn plus 1. So, but, okay, let's, but on the other hand, what happens if we swap now the role of x and y? So we can have this omega g n check, which we have to divide by dy over z1 to dy over zn. This gives you wgn check of, let's, y1 z1, yn zn. And what does this encode? This encodes, there's some here also about the length of boundaries of maps, which are now called fully simple. Ej, nj, which has now a different boundary structure, and this goes with y1 up to k1 minus 1 up to yn kn minus n. And it seems maybe an easy task to show that, but this was proven quite recently in a collaboration where Gaetan, Elba, Savarin, and another collaboration around Sergey and Boris. So this is a very interesting thing. Just this change of x and y gives you different maps here. And what I want to emphasize, here is the fact that this generating series are shifted. You don't have just the ordinary generating series, but this one, they're all shifted. And this is like the most natural thing to start with. We have to shift the generating series. This is also in free probability. You write the generating series in, but you should write it in this shifted version. Then everything is much simpler. No, this is the fact because these objects are actually differentials. And if you integrate them, the shift goes away because they are differentials. If you integrate, then you get here maybe then some ki, but then y to the ki. And here integration would give you some 1 over x I to the ki after an integration. Because we have to view these objects as multi-differentials and not as just the generating series, how it's usually defined, but they have like geometrically somehow the interpretation of differentials, and also if you shift them, all the functional relations as well are much simpler, much easier, and so on. Yeah, I think I will stop here and I will start the next tomorrow, the next lecture directly with showing you the functional relation between this W's check and the other W's. Okay, good. Thank you.
Okay.